Hi, it's Mr. Andersen, and this is AP Physics Essentials Video 60. It's on Newton's second law, which when expressed is probably the most important equation in all of AP Physics, F equals ma. Now on your equation sheet, there are a couple of things that are added to that. So we could express it like this. The net force, which is a vector, is equal to the mass times the acceleration, which is also a vector. And that net force and that acceleration are always going to be in the same direction. But what does it mean to accelerate? It means that if you apply a constant force to something, it will get faster and faster and faster over time. And the larger that mass is, that slower the acceleration is going to be. And so let's put a really large mass right here, and we're going to try to push on it. And so we're applying a force from the right to the left into this large object. And so where will the acceleration be? It should be to the left. But you could push on this as hard as you could, and it's never going to move anywhere. And the reason why is that there's a force in the other direction. So there's going to be this frictional force of this object that's opposing that motion. And so no matter how hard you push, there's going to be no acceleration. So if we could remove it, now we're removing that frictional force, and now we can get a net force in that direction. So just because you're applying a force doesn't mean there's going to be acceleration, because there could be opposing forces. But if we do remove those opposing forces, then we're going to start to get acceleration. That means it's going to start slowly, but it's going to get faster and faster and faster as long as we keep applying that same force. Another thing that's important to note is if you have two objects that are within the same system, even though one might be applying a force to the other, the system is not going to move. And so if you have a bicycle, even though there are lots of forces within it, there's going to be no change in the center of mass velocity. There's going to be no acceleration of the system itself. If we want acceleration of a system, then there has to be a force from one object outside that system on another. And if we apply that force, then there's going to be acceleration. The velocity is going to start increasing. And that acceleration, which is a vector, remember, is equivalent to the force, the net force, divided by the mass. Or we can just express it as force equals mass times acceleration. Now again, if we have one system with two objects inside it, and so I've got a little simulation here. We have two spheres. So think of this whole rectangle as one system. And so what I'm going to do is attach a spring between the two. And now I'm going to point to where the center of mass is, which is right between the middle. And so what I'm going to do is unpause the simulation, and there's no acceleration. That's because there's no force. There's no tension in the spring. And so now let me pause the simulation again. I'm going to stretch the spring. So now we know there's a force inside there. Where's the center of mass? It's shifted to the right. And so now let me unpause the simulation. And you can see that there's movement, but the center of mass is not moving. There's no acceleration there. How are mass and acceleration linked? Well, I've got a simulation again. On the left side, we've got this set, so it's not going to move. And so now I have two spheres, and if I let them go, nothing's going to happen because there's no tension. And so what I can do is I can stretch those two springs. They're identical springs. And now what's going to happen, again, if the left side is totally fixed, we're going to get acceleration in that direction. But did you see the acceleration was different? And so let's look at that again. So we've got two different accelerations. Acceleration of the orange sphere and the silver sphere. Remember, the force is going to be the same. The force in the spring is going to be the same. And so we get motion like that. So which one has a greater acceleration? We would say the orange sphere has a greater acceleration. So since the force is the same, what does that tell us about the mass of that object? The mass has to be less. Since it has a greater acceleration, it must have a smaller mass. And so the one on the top has a 5 kilogram mass. One on the bottom is twice that. And so when we let it go, the one on the bottom is going to have an acceleration that is half that on the top because it has a mass that's twice as large. And so to apply this, how do we measure acceleration in a simulation like this? Well, imagine if we have a 1 kilogram sphere and it's 4 meters off the ground. We're going to get acceleration as it falls down. But how do we measure that? Well, what we can do is use video simulation, or we could use a ticker tape, but what we can do is keep making marks every set amount of time. And so what I'm going to do is mark the center of mass as it changes over time. And so it looks like that. So you can see the distance between those marks is getting greater. So that implies that we're getting acceleration. In other words, it's moving. And so how could we figure out what that acceleration is? Well, if I graph it, we've now got the change in position over time, and you can see that it is increasing in the negative. And the distance between them is increasing, so you know the velocity is increasing in the negative as well. And so how could we figure out what that acceleration is? Well, remember, the slope of a position versus time graph tells us its velocity. You can see it's increasing here. But if we graph the velocity versus time graph, then we have a straight line. So that implies that we have a constant acceleration. The velocity continues to get greater and greater and greater in the negative. So if I calculate the slope of that, we're seeing a change of negative 8 meters per second during a 0.8 second period of time. And so if I divide my change in velocity over time, I'm going to get an acceleration of around negative 10 meters per second squared. And you know it to be about negative 9.8 meters per second squared. So now we know the mass, 1 kilogram. We know the acceleration, negative 10 meters per second squared. So could you figure out the force? Well, it's just plugging it in. If we know the mass is 1, the acceleration is negative 10, what's going to be the net force? It's going to be negative 10. In this case, it's going to be negative 10 newtons. It's going to be in the same direction that that acceleration was. And so what's causing that? That's the force due to gravity. It's the weight of the object. And so what would happen if we were to take that same 1 kilogram mass and we were to move it to the moon, where the gravity is 1/6 what it is on the Earth? And so what's going to happen to our force? It's roughly 1/6 of what it is here. So it's around 1.6 newtons. So the mass hasn't changed. We have negative 1.6 newtons. And so what's going to be our acceleration? It's going to be negative 1.6 meters per second squared. So it's going to take much longer for it to accelerate and eventually reach the ground. So solving problems using Newton's second law are very simple. So let's say we have a rocket and it's a 10 Newton force that's being applied to a rocket and it's a 20 kilogram rocket. Could you figure out the acceleration of the rocket? Well, for sure. So we've got 10 here, 10 newtons. What is our mass? It's 20 kilograms. And so we'd simply divide 10 by 20 and we're going to have an acceleration of 0.5 meters per second squared. But let's say that we apply that force to the rocket and then we just let it coast for a while. So I'm applying the force, we can see the acceleration, but let's say I turn the rocket off for a while. Could you figure out what that position versus time graph is going to look like? So again, it's accelerating to the right, so we should have a curved line, but then it stabilizes for a while. So the velocity stays the same for a while. In other words, it has velocity and it's just going to keep moving in that direction. So what would the acceleration versus time graph look like? Well, we have constant acceleration through here. The acceleration is getting greater. But what's going to happen once we get rid of that force? Once we remove the force, what happens to the acceleration? It should go to 0. And so the graph would look like this. Here's going to be an area where we have a constant acceleration due to that constant net force. But once we remove the net force, it's still going to keep moving. It's just not going to have any acceleration. So could you apply Newton's second law to solve problems? In this case, we know the force, we know the mass, we could solve for the acceleration. But if we know the acceleration and the mass, we could solve for the force. And then finally, could you use mathematical or visual representations to see if there's going to be a change in the center of mass of a system? I hope so, and I hope that was helpful.